Okay, so let's start today's session. Good afternoon, everyone, and welcome to this 10th interactive session. And this interactive session, as you all know, is for the NPTEL course named Experimental Physics Module 2. Course instructor for this course is Professor Amar Kumar Das from IIT Kharagpur, and I am PMRF Research Scholar Mrinalini from School of Physics, University of Hyderabad. So this is the 10th interactive session, and we conduct these sessions every Saturday 3 to 5 p.m. And as you know, these sessions are also being recorded that we upload on YouTube channel, and also these PPTs that we'll be discussing here, I upload this on the drive also, which you will be getting links for so that you can go through them later. And if you have any doubt in between, you can unmute yourself and ask the doubts. Okay. With this, let's start today's session, and we'll have a recap of last week's things that we discussed. So last week we had started discussing another phenomenon, which was diffraction, and we understood how light bends through the corners or through the obstacles when the wavelength of that obstacle or that gap matches with its wavelength. So this was the diffraction phenomena. And then we had discussed how a diffraction through single slit will give us the what we will see when we'll have a small opening and a parallel wavefront will come through it, what kind of interference pattern or what kind of pattern we will see. And similarly, what will happen when we'll be using a double slit diffraction. Okay, so in a single slit diffraction, we usually obtain this kind of pattern, maximum intensity at the center. Whereas in double slit diffraction, there are two things happening, interference as well as diffraction fringes. So we get overlap of diffraction and interference fringes. And then we had discussed Fresnel diffraction, where unlike Fraunhofer diffraction, so in Fraunhofer diffraction we had discussed that we have source of light and the screen on which we are going to see our image at infinite distance, and how we obtain that in lab is by using lenses, right? But this we had discussed Fresnel diffraction, where either the source of light or the observing screen or both are at some finite distances. So this also we had discussed the Fresnel diffraction, and then we had discussed how this Fresnel diffraction will give us the patterns if we are using circular aperture. One aperture could be like this, where the center we have gap and other area is blocked. Then we will get a circular ring kind of patterns, and another circular obstacle cases where the center it's opaque and around it the light can transmit, and still we will be getting fringes like this. Then we had discussed Fresnel's half-period zones, and we had done some derivations. After this experiment we were discussing for single slit diffraction and double slit diffraction. And yeah, so now continuing that, still the topic of diffraction, in today's session we will discuss a little bit about plane transmission grating. So the detail of this theory, again, you must have seen in this week's lectures that have been published. So we'll discuss few things in brief, and if you have any doubt you can ask. So diffraction grating experiment, the aim of this experiment is to first we'll see what is diffraction grating, and then based on this what kind of experiments we can do. So if you recall, like I was saying, when we have single slit, we were talking about that we have a screen or slit which has single opening, then light is passing through it and reaching the screen, and we are getting some pattern. So here it's only one slit diffraction we can see. If we have a slit like this where we have two openings, then From single slit there will be diffraction. From here also there is diffraction. Also what light is coming from here, also what light is coming from here, if they are coherent sources, then they'll interfere as well and we'll see some kind of pattern. So this is one slit diffraction, this is two slit diffraction. If we have a slit where we have more than these, like many number of slits, then we can call it N slit. N slit diffraction situation. And this thing actually we call, this is what we call grating. So grating is kind of a slit in which we have different small very close openings, you can say, ridges. That in this grating also we have reflection grating and transmission grating. So yeah, transmission grating. So in reflection grating they may have some kind of carving on that particular material from which the light will reflect, and the same place where not same place, I mean, but on the same side from where the incident light is coming, the image is also, or the pattern is also formed on the same side. This happens when we are using reflection grating. But when we have a grating which has very close and small openings, n number of openings like this, usually these are like few thousands or few hundreds per inches, or few thousands per centimeter number of lines or openings, then we call it transmission grating. So here we see similar example. This is a slit, okay, which has many number of small openings, and this, what are the conditions required to see diffraction through such kind of grating? First condition is Fraunhofer diffraction and not Fresnel. That means we need the lines wavefront to be parallel like this, and thus it needs to come from infinity. And how do we attain this in our labs? We use a lens, we have a source of light, we use our convex lens which makes it parallel when the source is kept at focus of this lens, right? This we have understood in first or second week of these sessions, that when we keep this source at the focus, the image will be formed at infinity. So this trick or this thing we are using to get the sources to be coming parallel. So it seems that they are coming from infinity. So our Fraunhofer condition is satisfied. This is first condition. Second condition is the incident light should be normal to this grating. So as I said, these are all coming from infinity and are at 90 degree to this grating. This is second condition. If these are at any other angle than normal to this slit, then we won't be able to use this simplified derivation that we have done. So that's why we are using this one, another condition. Third condition is, yeah, as I said, we have two type of gratings. One is we have. One is reflection grating, in which the incident light comes, hits and reflects back, and we get the pattern on the same side of the grating. Whereas another one is transmission grating. If I say this is reflection, then transmission, we have small lot of openings through which light comes and passes, and then they diffract and gives us some pattern. Okay, now this is the third condition that we are using here, transmission grating. We are going to discuss transmission grating. Now another thing is, what is this D? This D for gratings we call grating element. Okay, now this grating element is what? So again, if I explain you here, let's say, or when we were talking about two slit diffraction, say there are two openings in this slit right now. One opening, say its opening width is A. This also is same. Its also width is A. Now this opaque part which is between these two openings, say its width is b. Okay, in this case, if we want to say what is the distance between these two openings or these two gaps in the slit, then we, to define that, we take center of this opening and again center of this opening, and then the distance between the center of these two openings we call d. So as you can see, because we are taking center of this gap, if the gap width is a, then half of it will be a by 2. Similarly here also, the gap width is a, that means half of it will be a by 2. So b plus a by 2 plus a by 2, that is b plus a. This is our d, which is the distance between the two gaps. And this d, for gratings we call it grating element, which other places we were calling the distance between the two gaps or two slits. Here we call grating element because there are very high number of openings are there. Here we have shown only few, but actually, as I said, we'll see further also that there are like few thousands per centimeter, few thousands per inches kind of openings in number. So this is grating element. Now what is m? M is 1 over d, that is number of rulings per unit width of the grating. As I said, we have few thousands per centimeter, few thousands per inches. So those number of rulings per unit width we can define per centimeter or per inch. So per unit width of the grating, that is m, and it is inverse of the grating element value. Theta is the angle by which the light is diffracting. So we will get lot of parallel lights. What will happen, from this particular opening the light will diffract at theta angle, and we will be having lot of diffractions along the same angle, all parallel lines with theta angle. Then we will have some diffractions which will be theta prime, okay, and many lines parallel to that. Then we will have some lines diffracting at angle say phi, something other than theta and theta prime. Then there will be lot of lines parallel diffracting parallel to this phi. So in this way we will not only have lines parallel to theta diffracting and giving us pattern, we will have lot of number of parallel lines in this way, and thus we will be seeing many orders of patterns here. As you can see, if we use monochromatic light, then we may see something like this, and if we will be using a white light source which has various components of light in it, then we will see something like this with varying order. Okay, so what will be the condition for getting maxima? The for getting principal maxima, we will be, this is the path difference we have to get right. Path difference should be integral multiple of lambda. So the path difference here will be d sine theta, which will be equal to n lambda. So we can calculate lambda from this, which will be n d sine theta. Lambda will be d sine theta upon d sine theta upon n. N is the order. Resolving power also we can calculate for this, which will be given by lambda over delta lambda, which will be equal to n multiplied by capital N. Now what is capital N here? What we mean by capital N is number of lines in the grating. So M is number of lines per unit centimeter or per unit inch, but here capital N means all, not per unit length, just like all how many numbers of lines are there. Usually when we say how many lines, we usually mean, it may be that it is 2 centimeter or 5 centimeter grating, but maybe our incident light is only hitting it for 1 centimeter. Okay, in that case we have to consider only that lines in 1 centimeter. But otherwise we, in many numericals, we assume that if our grating is 2 centimeter, then light hitting is all 2 centimeter, and in that case we consider this n for like all the total number of lines in this grating. So this we need to keep in mind, that how much length of the grating our light is hitting. Okay, otherwise this is the total number of lines on the grating. So that's why this is the order. M is number of rules per unit width of the grating, and X is the length for which it's hitting the grating. If it is the whole length, then it will be total number of lines on the grating. Similarly, as we can calculate resolving power, we can also calculate dispersive power of this grating, which is given by d theta by d lambda, which will be n over d cos theta. So you can see, like based on these information, we can carry out in this experiment where we can use a grating, and if we know few these things, then we can find out the wavelength of the light that we are using, and we can find out resolving power of the grating we are using, as well as dispersive power of the grating that we are using. So this was the, I think this brief discussion is sufficient to understand plane transmission grating. And to understand how to conduct the experiment, you please watch the lecture of this week of week 10, where professor has very well explained and demonstrated how the experiment has to be carried out. So this is I think example of reflection grating, where the incident light is on this side and the reflected light from the grating is also on the same side, and here we see different order of patterns formed from diffracted lights. So this is 0th order, this is first order, second order, this is first order on the other side of the center. Okay, from diffraction and gratings, let's move to another interesting part of optics, which is when we talk about polarized and unpolarized light. Okay, so what do we mean by that? I think we should first come here when we are, yeah, just to this we'll discuss later, Malus law. But light, we know it has particle nature, sometimes it behaves as particle, sometimes it behaves as wave. But when we talk about light as an electromagnetic wave, we know that light is moving in particular direction, say x, then it has electric field and magnetic field associated, where the electric field and magnetic field are moving perpendicular to each other and perpendicular to the direction of wave light as well. So the electric field vector of light, magnetic field vector, and the wave vector, that is the direction of light itself, they all three are mutually perpendicular. Okay, and the magnitude of electric field and magnetic field keeps varying. At one point it's maximum, at another point it's minimum, and then it changes its phase. I mean, it goes in another direction, then comes back, and this gives us wavelength of the light. So this picture is clear. Okay, so when this happens, this electric field is not only varying in one direction. If say if I'm drawing this dot, what this means is, if say light is going into the screen right now, okay, in this, then electric field will be varying in this direction and this direction. Also, it will be varying in this direction, in all the possible directions. So we usually represent this. When we represent like this, what we means is, this is we call it unpolarized light, because it's electric field, and perpendicular to electric field we'll be having magnetic field also varying similarly like this. But usually magnetic field strength are so less than electric field strength that we usually avoid them or ignore them, and it's okay to do that. It won't interfere with any of our results here, so it's safe to do this. So here when we talk about the direction of light, if it's in the plane of this screen right now, then electric field is varying in this direction to this direction, this direction to this direction. This is what we are showing. It's going, this is electric field, it's going in this direction. I mean, it's varying, its magnitude is varying, which is vector, and then it comes this. So basically it's going in this and this direction. Similarly, this is only one side we are showing. It will be going in the plane also in all possible directions. Okay, and then we call it unpolarized. Whereas we call it polarized when, due to some reason that we'll see what happens to it and what we have to do to get, but there is something that we can do to this unpolarized light, after which again if the direction of light is in the screen, then the electric field vector only starts varying in only one direction, just this or just this. Or if the direction of light is this, then we usually represent it like this, like we were doing here. The direction of light is this, then electric field vector is only varying in this particular direction, or it's only varying in the perpendicular direction, that is in the plane, going in out in out. So either we represent it with this, or we represent by this is the direction of light, and then these dots we make to show that electric field vector still it is perpendicular to the direction of light, but it is in and out of the screen right now. So then we call it polarized, because the electric field vector associated with this EM electromagnetic wave is only varying in one particular plane of the wave, and that's why we call it plane polarized or line polarized. So this was just, I wanted to give you guys understanding of what do we mean by unpolarized and plane polarized light. I hope this is clear. Okay, now let's start with refraction, but something little different from refraction. So in usual, when we used to have our glasses, in glass we had earlier seen how refraction happens, that when we have an opaque object, light just reflect from it and it follows a law of reflection. And similarly we had seen when we have a medium which is transparent for the light, then instead of reflecting from it, it passes through it, but when it follows angle laws of refraction, and the light is said to be getting refracted through this glass slab. Now we have different type of materials apart from this glass, where so for this glass you can see one light is going in and one light is coming out. This is what we usually were seeing till now. Now what if I tell you that we have some other type of materials which again will refract the light, that medium will be transparent for the light to go through it, but instead of coming out as whatever went in and the same thing coming out, we'll be getting double rays coming out. Okay, let's come back here. So we have some sort of mediums where isotropic medium, when velocity of light in that medium is same in all direction. So if we have this glass, in whichever direction you pass this light, it will come out as single. But we have some other type of mediums which are anisotropic for the light. Why they are anisotropic? Anisotropy usually means in different direction the property is different. So that time we use anisotropy word. What is different in different direction? These are such mediums, okay, these kind of materials are such that when light passes through them along one direction, its property, which could be velocity of light, is different, and when I pass the light from another direction, its property changes. Unlike the glass that I showed, that if this is normal glass, light is passing through it, it's refract by some angle. If it will pass through this side also, refraction will be by same angle, because the property of light is same in all direction of this medium. But there are certain materials for which when the light passes through different direction, the property of light changes. So it's something like, you can understand, like I was telling when we have prism, and prism how it splits a white light into its different components, that we were calling dispersion of light, and that happens because refractive index of the glass was function of wavelength. That means for different wavelength, the refractive index was value changes, and because of this, the different wavelength which constitutes the white light, they deviate by different angle, and on the other side of prism, instead of seeing the white light, we were seeing all 7 lights, right? So it's something like this, that for different direction here, instead of wavelength, we are saying that for different direction, the light has different properties. Okay, so velocity of light when passes through these kind of medium, it's not same in all direction of this material. So these are the 2 type of medium, and we'll talk now what is the change that we see. Okay, so just sorry, excuse me. So as I just now told, polarization. Okay, so these materials are called double birefringent materials, or double refringence it shows, means double refraction it shows. Now what happens? So these isotropic medium, they are called velocity spherical, and this anisotropic medium, they show velocity ellipsoid. Now what happens? Again, this is just glass medium. Velocity of light in the medium is same, even if whatever direction the light is coming, it will refract by same angle and then come out on another side. It will be same. Doesn't matter for the light which side it's incident. From any side, it will behave the same way. And refractive index for that light in any direction of this glass material, it will be same. But we have some materials like calcite materials and quartz materials which are anisotropic for the light. They also look, this is like a calcite, photo of a calcite material this is, and this also looks, when we make it clear and use it for this particular birefringent material, they also look similar like glass to us, and for the light it's also transparent, but the glass is not a crystal. Okay, glass is not a crystal, but these are crystals, and thus they have certain ordering of unit cells in them. Okay, because of that, the various properties are different along different directions. So these calcite crystals and quartz crystals are 2 such types of materials that we use for birefringent, to see birefringent phenomena. And refractive index, which also influences the velocity of light, depends on direction of light as well as direction of electric field when they pass through these kind of crystals. Okay, so these crystals are called double refraction or birefringence crystal, because they show birefringent, that is double refraction. So what happens in these crystals is, this is coming some kind of light, this is linearly polarized, they have mentioned, but even if unpolarized light is coming in this kind of crystal, then instead of getting one same light as output, we will be getting 2 lines in output now, and both will be linearly polarized. That just now I explained, linearly polarized means the electric field vector will be varying in only one particular direction. It will stay put in one direction, its magnitude will also be same, and it will be varying in one direction perpendicular to the direction of light. These are 2 way this is possible. One way, when electric field is in this varying in this plane, and when it is varying perpendicular to this plane. But in both the situation, you can see it's still perpendicular or normal to the direction of light. So this 2 linearly polarized lights are possible, and thus when we use these special crystals, then input is unpolarized, but output is 2 polarized lights where the polarization is different. Okay, so this is just what happens when we use, instead of normal glass, we use these kind of crystals. Again, just to summarize, when we use our simple glass, which is not a crystal, whatever light is incident after refraction at this interface and then again at this interface, we get same light. But if it was unpolarized, we'll get unpolarized. If it was polarized, we'll get polarized. until there is some particular phenomena happening that we'll see later in today's session. But otherwise, whatever we get in, like this is short. If we are sending in single, then we will be getting single light out. But if we have these special crystals made up of calcite and quartz, then if we are sending single ray, we will be getting out two outputs. One is what we call ordinary light or ordinary beam, another we call extraordinary beam. Now we'll see what do we mean by this ordinary and extraordinary beam. So, well, as the name suggests, ordinary is what we see usually, and extraordinary has something, it's doing something extra which we don't expect normally, and that's why we call it that this is something extraordinary happening. So what is ordinary beam? As you know, we have laws of reflection and laws of refraction, right? And we expect that all lights follow reflection, these laws. So ordinary beam is, of course, that follows, that we see that it's following the Snell's law, which is very second condition of laws of refraction. But extraordinary beam, we see that it's not following the Snell's law. This is what we feel. And that's why we started calling it extraordinary. But later it was seen that even this is following the Snell's law, because the refractive index is different for this particular beam. That's why we think it's deviating from its law, but it is following law. Since its refractive index is different from the refractive index the ordinary beam is seen. Okay, we'll go into detail now. Let's understand what further. So we have these two type of materials popularly we use, calcite crystal and quartz crystal, which are uniaxial crystal. Uniaxial because only in one direction they have this different kind of extraordinary ray, in other direction they have ordinary ray. There could be biaxial crystals also, like mica is a biaxial crystal, where there are two directions. They don't need to be perpendicular to each other, but I'm just showing they have two directions along which the properties of the lights are different. I mean, extraordinary in these two directions and ordinary in other directions, something like that. So let's not get confused. Right now here only we'll be talking about uniaxial crystals, which are calcite crystal and quartz crystal. These crystals have one optic axis. So as I said, they're uniaxial means they have only one optic axis. For mica there will be two optic axes. Okay. Yeah, so mica is a biaxial crystal and it has two optic axes. Just for information, here we will be only focusing on uniaxial crystals right now. So let us consider three mutually perpendicular axes, say x, y and z. Okay, this x is out of the plane of the screen and y and z are in the plane of the screen. Then optics axis is considered, if we consider optics axis along one of the principal axis, then velocity or refractive index along optic axis is different than that along the other two principal axes. So if we take the optics axis as z, then we'll see that velocity or refractive index along z, optics axis is different than that along two other principal axes. Now these two crystals, calcite and quartz, so they both are uniaxial crystals of course, but still there is difference between them because one of them, that is quartz, is called positive uniaxial crystal, whereas the other calcite is called negative uniaxial crystal. So what do we mean by this now? Positive and negative uniaxial crystal. So for positive uniaxial crystal, the refractive index along the z-axis, let's call N3 we are representing, the refractive index along z-axis is what we are representing right now as 3. Just to keep it clear, like one of the direction we are calling optic axis, so that's why we are calling z. Otherwise it could be any of the axis depending on how we are cutting the material. So we call it positive when refractive index along z-axis or is more than other two direction. So N1 we have written, but we mean N1 and N2 both. Like along one direction refractive index is more than the other two direction. So velocity of light Refractive index is more means the velocity of light in that direction will be less. So velocity of light along this direction will be less compared to the velocity of light along other possible directions. When we talk about negative uniaxial crystal, example is calcite, then along z-axis or the optic, if we keep the optic axis along z, then along that z-axis the refractive index of light is less than along any other direction, and thus the velocity of light is faster along that direction. Okay, so this is what we mean by positive and negative uniaxial crystals. Okay, so when we view an image through calcite or quartz crystal, we see two images, whereas optically isotropic crystal, like a glass, shows only one image. So here you see only one light coming out, whereas this is a calcite and we see two images. Even the word calcite we see is doubled here. Okay, this happens when the optics axis is perpendicular. That time we don't see the light coming, two lights coming, but that we'll see why it's happening. We are seeing only one light coming because the optic axis is perpendicular here to the direction of light, but we see two images because the splitting is happening, ordinary ray, extraordinary ray, but they are along same direction, only their speeds are different. That's why we are seeing two images, but ultimately when we use this kind of crystals we see two images. Okay, so optically anisotropic crystals are called birefringent because incident light may be doubly refracted. When light enters into uniaxial crystal, it splits into two orthogonal linearly polarized light rays. As I told, what we get out of this is both are linearly polarized but are perpendicular to, their polarization is different. Their polarization directions are perpendicular to each other, right? This is what we mean here. Now, what are these two rays that we get? One we call O ray, ordinary ray. One we call E ray, which is short for extraordinary ray. Something different is happening in here. O ray is sigma polarized. What do we mean by sigma polarized? If the direction of light is this, then electric field is varying in this direction. That means perpendicular to the plane right now. This is sigma polarization. And another thing is pi polarization, where if this is the direction of light, then the electric field vector is varying in perpendicular to, of course, this direction, but in the plane itself. So as you can see, these both are different and perpendicular to each other. So this is called sigma polarization, this is called pi polarization. Ordinary ray velocity is same in all directions, and that's why it's ordinary, because it just follows the same thing. So velocity is same in all direction because refractive index is same in all direction for O ray. Whereas for E ray, velocity depends on the direction because refractive index depends on the direction. We'll further see in detail which direction what we get. Velocity or refractive index is same for O ray and E ray along the optics axis. But apart from optics axis, along any other axis, the O ray, E ray, their refractive index and thus the velocity is different. Okay, so we are sending unpolarized light, we are getting ordinary ray and extraordinary ray. If we'll keep the optics axis, the incident light is going along the optics axis, if say the optics axis of the material is along this, then we'll not see any two rays coming, we'll see just single ray coming out. Okay, because the velocity and refractive index is same for O ray and E ray along optics axis but different perpendicular to this optic axis. Okay, so this is O ray, it is sigma polarized, its velocity is same in all direction, and then we have E ray which is bipolarized and its velocity depends on the direction. So for calcite crystal, which is a negative uniaxial crystal, refractive index for O ray is 1.6584 and refractive index for E ray is 1.4864, which is less than the refractive index for O ray, and thus velocity of O ray is less than velocity of E ray. So this happens for negative crystal, and for quartz crystal, which is a positive crystal, refractive index for O ray is less than refractive index of E ray, and thus velocity of O ray is more than velocity of E ray. Okay. Now if we take, as I said, there's an isotropic medium. Isotropic medium shows velocity spherical behavior, and an isotropic medium shows velocity ellipsoid. Now what do we mean by that? See, we were talking about three axes, right? That x, y, z axis, and one of the axis we'll consider optic axis. Like here, let's say the optic axis is along z axis. Let's assume we can consider any of the directions. Here we are taking optic axis along z axis, which for if xy I am making in the plane, that means z axis is out of the plane. So as I said, optic axis is along z axis. That means in these two axes, what happens is the refractive index of E ray and refractive index of O ray will remain same, right? Refractive index is same for O ray and E ray along optic axis, but different perpendicular to optic axis. So their refractive index and velocity is same. So here what is happening is their velocity is different because this is not optic axis, right? Optic axis is z. So this is apart from optic axis. So their values are all same in this plane, but their magnitudes are different because refractive index for them is different along x-axis and y-axis, but they are same in this plane. When I plot y and z, now z is the optic axis, so here the velocity and refractive index for both E ray and O ray is same, so that's why they match here at the same point. And then this, if I'm saying this is for calcite, then for calcite we know velocity of E ray is more, so velocity of E ray is more, and velocity of O ray, which is anyway same in everywhere, so it will remain like a sphere. But for E ray, it's behaving like a ellipse. And same what is happening when I change from x to z, the same elliptical behavior. Whereas when I take a positive crystal, when I plot in xy plane, if z is the optic axis, then for positive crystal, velocity of E ray is less. So E ray magnitude, this is velocity magnitude actually, okay, along x-axis and y-axis. So velocity of E ray is less, velocity of O ray is more for positive quartz crystal. This was for negative quartz crystal. Okay. And when I plot between z and y, then the refractive index of O ray, it will always be a circle for O ray because its value is unchanging. But for E ray, when it comes along z axis, its velocity is less, whereas along y axis, its other axis, it's more. So this is the different ellipse and circular behavior we see. For polarization by double refraction, there are different cases. For calcite, especially if we discuss, just let me have some water and let me see what it is going from. Just to see the recording is happening fine. Yeah. Okay, so polarization by double refraction. Assume that this is my not glass slab, but this is my calcite crystal slab, in which the optics axis is along these dotted line. Optics axis, when we say, if I have a slab, say it is made up of calcite crystal, okay, and if this is the optics axis, this shape, like apart from all the crystal, if I cut a slab like this, and maybe the optics axis was like this for this material, okay, and I have cut out this slab, then this slab will have optics axis like this. If I cut out the material such that optics axis is parallel to the edges of this rectangle, so like depending on, and if I cut it out in some, I mean it depends how I want, or if I cut it out like this, then it will be like this. So out of that material, it depends how I'm cutting out my required material slab, So the optics axis will be, it may be different direction. At one time it could be like this, and my incident light is coming here. So for incident light, optics axis is normal or perpendicular, whereas if my optics axis is like this and my incident light is coming like this, then it will be parallel to the optics axis. And another case could be it's in some random direction and my light is hitting at particular angle. So there could be various direction in which the optics axis can be oriented, because the material, the structure, that geometry I have cut out from the bulk material, that may be different. Okay, so don't get confused that optics axis has to be parallel to one of the edges. Okay, so if my optics axis is in this direction, particular direction, okay, in this direction, so we are just representing here that it's like a hole in this direction we mean. Okay, and this comes my unpolarized light. How we know this is unpolarized light? Because we see these arrows show the E vector is in this direction, and these dots show the E vector is in the plane also. That means this is not linearly polarized, means this is polarized, because the E vector is in all possible directions. So this is unpolarized. Okay, and as it enters this calcite material, there will be refraction. Now from law of refraction we know that angle of incidence is equal to angle of reflection. This is from law of reflection. From law of refraction we know it depends, mu sine I is equal to mu of second material, this was mu of first material, sine R. That is depending on, it depends on refractive index, because this directly I is not equal to the refractive angle, but there is influence of refractive indexes also. So here if it's coming like this, since it's coming at 0 angle, it should go just pass through it at 0 angle. That is what we expect from the usual law, and that's why the one part of this light, it when it enters, it will split into two parts. One part will go directly, this we call O ray, and another will split and go in some other direction, this will be called E ray. Why E ray again? Because you see this is following Snell's law, that the angle is 0, angle of incidence is 0, so angle of refractive angle should also be 0, but this extraordinary ray, we see that it's doing something else. That's why we started calling it extraordinary ray. But from later it was got clear that this light we are seeing, it's at 0 angle considering this normal, right? But for this E ray, it is also following the law of refraction, but for it the normal has to be taken not perpendicular to this slab but perpendicular to this optics axis. If we take that, then we'll see, if this is my optics axis, if I take perpendicular to that, then I'll see that this is the angle of incidence, and then I'll see that this is the angle of refraction, and we'll see that this is same. Okay, I mean this just to explain you that even this is following angle of law of refractions. It's just the changes that earlier we used to take this angle of incidence from normal to the plane, normal to this, right? But now we have to consider that it normal we have to draw to these optics axis direction. Okay, we are not going in detail of that, but just to clarify, I told you this portion. Even if you didn't understand, okay, we can do this. But what you have to keep in mind is when we send unpolarized light through this crystal, uniaxial crystal, it splits into two parts. One is ordinary ray, which passes as it comes, and another part goes in another direction, and that's why we call it extraordinary ray. If now the slab or the material is such that the optics axis is in this direction, okay, the optics axis is in this direction, and the light incident, unpolarized light incident on this material is parallel to this optics axis, then it will pass without splitting. Why? Because we had seen that velocity for O ray and E ray is same along the optics axis. So along the optics axis, velocity of E ray, O ray both are same. So as the unpolarized light is coming, it will remain same and come out of the material without any change. And this I already explained why we can have different directions of optic axis in a same looking rectangular slabs, because we are cutting out from in different fashion so that we can have the optics axis along different directions. Okay, so another case here, the optics axis and incident ray, the angle between them was 0, right? Now this is the incident unpolarized light, and now optics axis is normal to it. It means that difference between incident angle and optics axis now is 90 degree. So here also there will not be outside the material, there won't be any splitting, but we'll see something like this case, as I was outside only one we'll see, but inside something will happen. That is because only along optics axis E ray, O ray have same velocity. In other directions they have different velocity. But I'm sending light at 90 degree to this, right? Sorry, 0 degree, because we measure from the normal, and to the normal this is making 0 degree. This 90 degree, don't confuse this 90 degree, I'm talking about incident light and optics axis 90 degree. But this angle of incidence from the normal to this interface, the angle is 0 degree. Here also normal to the interface, the angle is, what is this? Normal. I don't know why this keeps on happening. Wow. Sorry. So the angle is 0 degree. So refraction is also 0. Here the angle of incidence is 0 degree. So light is not going anywhere. It's also come out in the same direction. But since optics axis is along this direction, so perpendicular to that direction, the E ray, O ray will have different velocities. That means one light entered. Now here they split into two parts. These two lights are going along same direction, but these two parts have different velocities. So one part is going faster, another part is going slower. So this is what is happening here. Okay, so this was it. And then, so refractive index for O ray we can define like this, and refractive index for E ray we can define like this. Okay. Now, what is the use of these kind of situation? So the use of this birefringence is, we make a device called Nicol prism. The Nicol prism is an optical device for producing and analyzing plane polarized light. When ordinary light is incident on Nicol prism, it splits up into O ray and E ray. These two are completely plane polarized, of course, with vibrations in mutually perpendicular planes. So Nicol prism is a device which we use to produce plane polarized light. That means what goes is unpolarized, as you can see here. It's unpolarized, and out of this Nicol prism, what comes out is polarized light. Okay, and that too they come out different. Ordinary ray, extraordinary ray, we get far away so that we can use, like we can detect one and exclude the other one. So what we do in this is, we take one prism like this. You can see this is one prism. Okay, this is another prism, and we paste them using this cement called Canada balsam. This is a special kind of cement which is still transparent to the light, but it's still able to join these two prisms. Okay, this is a special kind of cement. So again, a Nicol prism, which is an optical device made from calcite material, which is a negative uniaxial crystal. Functions as a polarizer by splitting unpolarized light into ordinary and extraordinary rays then eliminating the ordinary ray through total internal reflection, leaving only plane polarized extraordinary ray. So what is happening in this is, these are two calcite prisms that we have pasted using Canada balsam. Okay, this is unpolarized light hitting and coming in this Nicol prism. Okay, as soon as it comes here, if it's not the optics axis, then it will split. Sorry, then it will split in as O ray and E ray, and then what happens is, this, if it is made up of calcite, then for calcite O ray refractive index is higher, and this Canada balsam cement, its refractive index is less actually. If you see, for O ray refractive index is 1.6584, and for this Canada balsam cement refractive index is 1.55. Okay, so when this O ray comes, this is the O ray that is coming. Now it's already polarized also. Okay, and its O ray is, sorry, there is O ray is sigma polarized. Okay, like this. As you can see, this is O ray. It is sigma polarized. You can see E vector is perpendicular to the plane of the screen. So this is O ray, and this is for O ray. This is denser medium, and this Canada balsam is rarer medium for it, because refractive index is less. So for this O ray, this material is denser, optically denser than this Canada balsam area. So when it's coming from denser to rarer medium, if you remember the situation, when light is coming, outside is air, when we used to discuss total internal reflection phenomena, if you remember. So light is coming from glass and it wants to go out to air. So it will go away from the normal. Okay, if I increase the angle more, there will be a situation when it will go parallel to the interface, and there will be a critical angle, okay, at which the light will come back. Instead of going out, it will just come back inside the same glass material. That time we used to call this phenomenon total internal reflection. Same thing what is happening here. At particular angle, for this O ray, it's coming from denser to rarer medium. At particular angle, it will suffer total internal reflection, and it will not come out here, which we were saying that usually in calcite crystal we'll send one ray and two plane polarized rays will come out. But why here we are saying only one ray? Because we have made this special kind of arrangement which we call Nicol prism, where we have pasted these two together using Canada balsam cement, which has less refractive index. Okay, so for O ray, this is denser to rarer, and it's suffering total internal reflection, so it's not coming out here. But for E ray, for which this calcite material refractive index is 1.4, but it sees that, E ray sees that Canada balsam is optically denser medium because its refractive index is 1.55. So it has no scope of total internal reflection, and it just crosses, refracts, and ultimately refracts here as well, and then come out. So what we see is, if observer is here, he or she will see that incident was unpolarized, and output is this pi polarized ray, which is E ray. So this is what we get out of Nicol prism. So what Nicol prism is doing? Nicol prism is taking unpolarized light but giving output as plane polarized light. So this is like a device. If we want to make plane polarized light for some purpose, then we can use something similar as Nicol prism. Similar to Nicol prism, we have different kind of prisms like this Rokon prism. Okay, what we do here, again we will be using calcite, and the refractive index for ordinary ray is more than E ray. This we are talking, of course, along the optics axis, all the refractive index is same for both, but in other directions it's different. Okay, now here we again make the same kind of arrangement and we paste these two together using cement, balsam cement, Canada balsam cement. And then here what we see is, for one part, optics axis is in this direction and incident light is parallel to this. Whereas for other part that we have pasted, the optics axis is perpendicular to the plane of the screen right now. Okay, it's perpendicular to the screen. So these two have optics axis along different direction. So what happens? We are sending unpolarized light. It's going parallel to the optics axis. That's why E ray, O ray both have same velocity. So till here no splitting is happening, no slowing down, nothing. It's just passing. Why? Because from the normal to this surface, the incident light is making zero angle, so no refraction, nothing, is just passing simply. Okay, but after this they encounter this joint. Now the optics axis is not anymore parallel to this direction. Okay, so E ray, O ray get separated. This is one kind of arrangement. Okay, similarly this is, so this, from this also we can see that O ray is, we can call a ray O ray when it's sigma polarized, that is its electric field vector is perpendicular to optics axis, and E ray we can call the ray which is pi polarized, that its electric field is parallel to the optic axis. This is another kind of arrangement for same Rochon prism, that again incident light is coming and optics axis is parallel to the incident light, so no splitting is happening up till here. Only when it encounters the another part of this prism, where the optics axis is now perpendicular to the direction of incident light. So O ray, whose velocity is less, will slow down, and E ray, whose velocity is more, will, so that's why they'll split up. Okay, like this. Another kind of prism arrangement is there, which is called Wollaston prism. In this, we have one part of prism where optics axis is perpendicular to the direction of light. This is the direction of unpolarized light. Optics axis is perpendicular to it, and another part, optics axis is perpendicularly out of the screen. So again here, what happens at this point of time? Because the optics axis is perpendicular to the direction of light, so no splitting is happening, but direction wise no splitting is happening, but the component is splitting into one part which is slowed down, which is O ray, another part which is E ray, which is going with the higher velocity, and from here they again change the direction because the refractive index for them is different. And what happens actually is, here O ray becomes E ray and E ray becomes O ray. So this is what Wollaston prism does to the unpolarized light. Okay, so again further, like Nicol prism that we used to make unpolarized light, to obtain polarized light, we use something known as retarders. Okay, what we do with retarders, these are some kind of devices where, let's say this is my material made up of these kind of crystals. This is unpolarized light hitting it, this is optics axis, and this material has some thickness d. Now optics axis is perpendicular to the incident light, right? You can see the angle between them is 90 degrees. So what will happen? We'll not see them splitting in different direction, but we'll know that some part of it will, its velocity will get reduced, whereas the remaining part of it will have higher velocity. So what happens here is, when they come out, these O ray and E ray, when they come out, now outside they have same velocity, they will get same velocity, right? Because outside it's air, but inside where this special crystal was, there they, direction wise they were not splitting. Again I'm reminding, direction wise they are not splitting, they are following the same path because the angle of incidence was 0. Okay, so they are following the same direction, but some part of the ray, its velocity was reduced, another part of it the velocity was still more. So what will happen, depending on the distance they travel or depending on the width of this material, which we call d, there will be some phase difference in these two parts of the same light, which will again combine when they will come out. And if the phase difference or the path difference, which we can give by, this is refractive index for O ray, this is refractive index for E ray, and this is d, which is the thickness of the path which they are covering. So path difference for these two parts of O ray, E ray, path difference between these two rays will be n naught d minus NED. This will be the path difference between O ray and E ray when they combine outside. We can simplify it to write like this. Now we know phase difference is 2 pi by lambda times path difference. So if phase difference, it depends on d, you can see phase difference is depending on d. So if somehow I keep the d such that phase difference is pi by 2, okay, if phase difference is pi by 2, that means path difference will be lambda by 4, and I'll get a device called as quarter wave plate. Quarter wave plate. Okay. Quarter wave plate means the path difference between these two parts of the ray will be lambda by 4. So this kind of device is called quarter wave plate. If I keep the distance or the width of this material such that the phase difference between them is pi, then path difference between them will be lambda by 2, and then we'll call it half wave plate. We are calling it plate, like wave plate, half wave plate. We are calling this device. That means the O ray, E ray will have lambda by 2 path difference. If again there will be a situation or D will be such that phase difference between them will be 2 pi, then path difference between them will be lambda, and we'll call it full wave plate. So using this phenomena and the direction in which we are making the line incident respect to the optics axis, here the optics axis was normal to that direction of incident light, we can get these different kind of path differences between these two O rays, E rays, and outside when they come they will have some path difference, and thus they can behave as quarter wave plate, half wave plate, or full wave plate. So this is another application of this birefringence. Okay. Now moving on to further, I had started explaining that light is an electromagnetic wave. It has electric field, magnetic field components mutually perpendicular to each other as well as perpendicular to the direction of propagation. As you can see here, this is the direction of propagation. Electric field and magnetic field here is out of the plane. So if this is x-axis, electric field is along y-axis, as you can see here. Then z is out of the plane, which is the direction for the magnetic field. And since strength of magnetic field is very less than electric field, so we just usually don't represent it when we talk about polarized light. So electric field is varying in this direction. Okay, it's varying in this direction. When it varies in all the direction, we call it polarized. And when we use these special crystals, then we get we restrict the electric field variation in only one direction, and then we call it plane polarized. Either it becomes like this, or it becomes like this. Okay, then we call it plane polarized. So unpolarized light we represent by this, and polarized light, which we call linearly polarized or plane polarized, we represent by this or this. So this was about polarizing a light. Now what happens is, again there are different type of polarization. This linearly polarized, or also that we call plane polarized light, orientation of electric field is constant. Okay, this is the wave vector, that is direction of light, and electric field magnitude is same, and its direction is same, either this or this plane of vibration. Then if this electric field is varying in different direction, I mean it's different from polarized light because it's difficult to explain this in 2D, but the tip of the electric field vibration is rotating, so it's something like this we see. And from the front, if you see, you will just see circular, instead of electric field varying in one direction, we see one time it's in this direction, another time it's this direction, so it's forming like this. How is it different from unpolarized? Because in unpolarized, at particular point of time, all these were existing. This was varying in this direction, this was varying in this direction, so many such directions at simultaneously the electric field was varying. But in this, at one point of time it's here, then after some time it's here, after another time it's here. It's not simultaneous. Okay, it's, but when I see from here, I see ultimately it's circular. So that's why we call it circular. And if the magnitude is also varying, it's here it's more, here it's less, here it's more, then I'll see as an observer, when I see from here, when I see from here, I'll see it as varying as an ellipse, and then we call it elliptically polarized. Okay, and then depending on its it's going in this direction or it's this direction, we call it left-handed or right-handed, that is clockwise or anti-clockwise. So these are different types of polarizations that we get. Now what we see is, if we are sending unpolarized light through this device which polarizes, okay, this kind of crystals or prisms, then if the optics axis is parallel to the electric field vector, then the light will pass through it and the electric field parallel to the optics axis will remain. Other electric field variation directions will not be there. So we'll get plane polarized light, and when we pass through again this same device, then if again the optics axis for this particular material is parallel to the electric field variation direction, then all the light will pass and we'll be able to detect in the detector all of it. But if the analyzer's optics axis is at some particular angle to this electric field vector variation direction, then we will not get all the light. Okay, we will only get I cos theta. If incident is I naught, okay, if I naught is coming here, sorry, here some higher intensity was there, now only the electric field coming out parallel to the optics axis of this device is coming here, so it will be some I naught. And that I naught also, depending the analyzer's optics axis, we'll get I naught cos theta, I naught cos square theta actually. Okay, so this law is called Malus law. So the same material actually we are using, it's not, but this we call polarizer because it's polarizing the unpolarized light, and when we keep it after the polarized light, then we call it analyzer because it helps us analyze the direction of polarization. Maybe I don't know for this polarizer what is the optics axis direction, but if I keep analyzer, okay, and if their optics axis is parallel, what I mean is if optics axis of polarizer and optics axis of analyzer both have optics axis parallel to each other, then I'll see maximum intensity of light coming out. And if they are perpendicular to each other, then cos 90 means 0. I will not see any light outside, and the intensity varies with I naught cos square theta, and this law is called Malus law or Malus law. So intensity varies, I is equal to I naught plus a minute. Yeah, the information is getting hidden here. So electric field becomes E cos theta, and this is amplitude. When we take square of it, we get intensity. So we get intensity variation as I naught cos square theta, and this is our Malus law. And this is it variation we see something like this. At 90, 180, it becomes 0 because polarizer, analyzer their optics axis become 90 degree to each other. Otherwise, we'll be seeing some intensity varying as cos theta. Okay. Okay, so this is another thing now, Brewster law. So what happens here? Here we were seeing we have some material through which when the unpolarized light was passing, it was getting polarized. This is what we have been seeing for this kind of special Nicol prism, that unpolarized light is coming, and what I'm getting here is polarized light. So here it was passing through the material. Now we have also the situation where by reflection itself I can get polarized light instead of transmission or refraction. So here what happens is a particular angle here is required. It's very important. This happens at particular angle, not for all the angles. At particular angle, the incidence unpolarized light, when it reflects, it becomes sigma polarized. At that particular angle, what happens is this reflected and refracted lights are at 90 degree to each other. When this situation happens, then this reflected light is polarized, and so what happens from Snell's law, we know this, all these angles theta, this phi, refractive angle, reflection angle, and this angle between polarized and reflected and refracted light is 90 degree. That means sine phi is 90 degree minus theta here, right? Because this theta plus 90 degree plus phi will be 180 degree because it's angle of this straight line, and theta plus phi will be 90 degree. That means phi will be 90 degree minus theta. So sine phi will be cos theta, mu will be sine theta upon cos theta, that is tan theta. This is called Brewster's law, and theta, Brewster's angle, is given by tan inverse of refractive index. So what happens here is, again, maybe we can discuss it again next week because one part of this is due in next week's lecture. So just to summarize that, instead of getting plain polarized light only after refraction phenomenon, we have one situation, this phenomenon where we can get a light polarized just by reflection. But it doesn't happen at all possible angles. It happens only at a particular angle, and this angle, at this angle, the reflected ray and refracted ray, they have 90 degree between them. Then in this situation only the reflected light is polarized and it is sigma polarized. Okay, and this law is called Brewster's law. Okay, so these were various phenomena that we have discussed. Now we have half an hour left, so I think we should discuss numericals which are important for you guys to solve your assignments due. So let's start with the assignments. So the question is the critical angle for a transparent crystal. So be careful, we are not anymore talking about glass because glass is not crystal, and glass was isotropic in nature, but now we are talking about these crystals which are mostly, I think here we will be discussing about uniaxial crystals. Okay, so the critical angle for a transparent crystal is 30 degree. Calculate the polarizing angle of the crystal. So critical angle is 30 degree, means at 30 degree when the unpolarized light is coming. Okay, no, actually this is critical angle means, critical angle means for total internal reflection. Okay, that at critical angle of 30 degree it's giving total internal reflection, or I mean it's going like this, not here, it's just going like this. So this is the critical angle of this material. Then we have to find out the polarizing angle. What do we mean by polarizing angle? The angle at which the reflected light, this will also be same, but the reflected light will become polarized and it will be sigma polarized. That means like this. So one thing we know from Brewster's law, we know that this polarizing angle or Brewster's angle is tan inverse refractive index. That means the polarizing angle is tan inverse refractive index, but we don't know refractive index. But we can find out refractive index since we know critical angle. The relation between critical angle and refractive index is this. Okay. So what will be refractive index here? It will be sine theta c. Theta c, the critical angle is 30 degree. Sine 30 degree is half. So this will be 2. Now polarizing angle or Brewster's angle will be tan inverse. Refractive index is 2. Tan inverse 2. Now what is tan inverse 2? Tan inverse 2 is, if we use our calculators, let me see, scientific calculator. So I need tan inverse 2, which is 63.4 degrees. 63.4 degrees. So polarizing angle is 63.4 degrees. B is the correct option. Okay, now question number 2. Refractive index of a glass. Now here we are talking about a glass. So refractive index of a glass is given to be 1.5. A ray of light incident on the glass, this is the glass, a ray of light incident on it, and its reflected light gets completely polarized. When it reflects, it completely becomes polarized. Find out the angle of refraction. Now I need to find out the angle of refraction. This is the incidence angle. This is same because it follows law of reflection. So this is same. And this is refractive angle. Now we know when incident light after reflection becomes completely polarized, that means this is Brewster's law phenomena. That means this happens when the angle between reflected light, this is our reflected light, and it becomes, so this was unpolarized and this has become polarized. Okay, this happens when angle between refracted and reflected light is 90 degree. Okay, now how we'll use this is, polarizing angle we know is tan inverse refractive index. We'll calculate this. Tan inverse of 1.5 means 56.3 degree using the scientific calculator. Okay, now we need to find out R. Now here again you see this whole thing is 180 degree. This whole thing is 180 degree. Okay, this IP plus these, I told you this becomes polarized when the angle between refracted light and reflected light is 90 degree. This happens then. So this is 90 degree plus refraction angle. This whole thing is 180 degree. So IP plus R is 180 degree minus 90 degree, which is 90 degree. Now IP I know is 56.3 degree. So R will be 90 degree minus IP, which is 90 degree minus 56.3 degree. This will be 90 minus 56.3. This is 33.7 degree. So for this particular situation, the refractive angle would be 33.7 degree, which is option C. Okay. Now next question. Question number 3. A ray of light is incident on a glass plate. Again, the glass plate's refractive index is √3. Is this side, if we assume it's air, refractive index will be 1. Okay. Ray of light is incident on a glass plate at polarizing angle. Okay, so it's incident at the polarizing angle. If it's incident at polarizing angle, means the reflected light will be polarized. Calculate the angle of incidence. Okay, we know polarizing angle it's hitting at polarizing angle, and polarizing angle and the relation between refractive index is given by this. Now tan inverse root 3 means 1.73. So tan inverse 1.73 gives tan root 3 is actually 60 degree. So the polarizing angle or the incident angle is 60 degree. That is option B. So these are very quick questions based on the formula that we have to keep in mind. Next question, the angle between the polarizer and analyzer is 60 degree. Okay, that Malus law, keep in mind. Unpolarized light is coming, there is a polarizer, its optics axis along whatever it is, the light will get polarized along that direction, and then we have analyzer. Depending on which direction the optics axis we rotate, we'll get intensity outside accordingly, okay, which will be varying as I naught cos square theta. A quick summary. So if the angle between polarizer and analyzer is 60 degree, that means theta is 60 degree, what will be the intensity of transmitted light? If the initial intensity is I naught. If initial intensity is I naught, then later intensity will be I naught cos square 60 degree. Okay. Now cos 60 is 0.5. Cos 60 is 0.5, so square of 0.5, which will be 0.25. So 0.25, that is 1/4 of the incident light it will become. So transmitted light's intensity will be 0.25 I naught. A is the correct option. Next question. Now, so these were questions based on Brewster's angle and Malus law. Now we have questions based on our gratings. Two lines in the fourth order spectrum formed by a plane grating are just resolved. So we have a plane grating, okay, and we are talking about fourth order, and two lines are just resolved, okay, and for resolving we know what is the formula. Resolving power of a grating, the formula is given by lambda upon delta lambda, which is also we call as this is the order and this is the number of lines on the grating, okay. So further, if the lines are due to wavelengths, these two lines which are just resolved, these two lines are 5890 angstrom and 5894 angstrom. Find the number of lines on the grating. So we have to find out this. This is the resolving power formula. We know lambda, delta lambda, n, which is 4. We need to find out total number of lines on the grating. Now lambda, we have two values here. Then what value should we keep? So in this situation, what we do is we take average of these two. Okay, we take average of these two. So here it will be 5890 plus 589294 divided by 2. This will be 5892 angstrom. Just let me confirm. 5890 plus 5894 divided by 2, 5892 plus 5892 angstrom. So we'll use this averaged wavelength here. Okay. So 5892 divided by the difference in these delta lambda is lambda 2 minus lambda 1, which will be 4 angstrom. So here we will have 4. N is fourth order. We need to find out total number of lines on the grating. So when we will solve this, we will get 5892 divided by 4 times 4. When we will do the maths here, we will get 5892 divided by 16, which is 368.25. So we cannot have 1/4 of line, so we can round it off to 368 number of lines. So total number of lines on grating is 368. B option is correct. Next question is, the sodium yellow light of wavelength 5893 angstrom is a doublet, we know D1, D2 lines, of 6 angstrom width. We know it has doublet lambda 1 and lambda 2. The difference between them is 6 angstrom, and this average value we are taking 5893 angstrom. What is the minimum number of lines a grating should have to resolve this doublet in the third spectrum? So we know 1 spectrum, 2 spectrum, 3 spectrum, many order of spectrum we will be getting from the grating. What is the number of gratings we should have on this, number of lines we should have in this grating, so that these two wavelengths should get resolved in the third order spectrum? Again, using our formula of resolving power, which is lambda upon delta lambda is equal to n, which is order of the line, order of the spectrum we are talking about, and this is the number of lines on the grating. And lambda 5893 angstrom. The difference between them is 6 angstrom. Order we are talking about is minimum number of lines grating should have to resolve this doublet in the third spectrum. That means we are talking about third order. Okay. So n, when we will calculate, we will get 5893 divided by 6 times 3. 5893 divided by 18. This is 327.388. If we will round it off, it will be 327 number of lines we should have at least, so that these two wavelengths will be resolved in third order. Okay. Now question number 7. A grating which has 5500 lines per centimeter. So I was telling you in the beginning that there are many lines. For 1 centimeter there are 5500 lines. So this is what we give as m, number of lines per unit width, which is equal to 1 over grating element, right? So a grating which has 5500 lines per centimeter is used to produce a spectrum of light from this mercury vapor lamp. What will be the angular separation of two yellow lines of wavelength this and this when viewed in the second order? So what is happening? From the grating, at the center there will be something, and either side of it we will be getting yellow line, okay, and we have to see their separation, angular separation we have to calculate. When in the grating that we are using, okay, the grating that we are using, it has 5500 lines per centimeter. This is its n value, and we know grating element D is given by 1 over m, okay, and we know condition for maximum also. When we are using transmission grating, the condition for maxima is d sine theta is equal to n lambda. Okay, so here we are given two wavelengths, so we'll get two conditions. So for lambda 1, the condition we'll get d sine theta 1 is equal to n. Now what is n? We are talking about second order, that means n is equal to 2. So 2 lambda 1, that means D is grating element. Okay, so D is 1 over m, which is 1 over 5500. Okay, so 1 over 5500, and sine theta 1 we don't know right now, and 2 times lambda. This lambda 1, let's consider this lambda 1, and let's consider this lambda 2. And we need to find out angular separation between them. So this is 5770. D is in centimeter, right? D is in centimeter, because this was 5500 lines per centimeter. So this is in centimeter, so I'll convert this also centimeter. In meters it will be 5770 times 10 to the power minus 10 meters. When I will convert it into centimeters, it will be 5770, because 1 meter is 100 centimeters, so it will become 10 to the power minus 8 centimeter. So 10 to the power minus 8 centimeter. Now all the units are same. Now when I further solve it, I will get sine theta 1 is equal to 2 times 5770 divided by, no sorry, multiplied by 5500, 6347000, 10 to the power minus 8. It will be 7654321, 6.347. So theta 1 will be sine inverse of this, which will give us 39.397 degree. This you can calculate from calculator. So this theta 1 we got for 5770 angstrom wavelength. Now for second wavelength, another slide for this. Yeah. So for lambda 2 now, lambda 2, which is 5791 angstrom again. So we'll use d sine theta 2 is equal to n lambda 2. So sine theta 2, and d is this 1 over 550, n is 2, lambda 2 is 5791 times 10 to the power minus 8 centimeter, because d is also in centimeters. And we will solve this. We'll get sine theta 2 is equal to 2 times 5791 multiplied by 5500, which is 6.3701, and theta 2 will be 39.569 degrees. Okay, so we have to find out angular separation. That means theta 2 minus theta 1, which is 39.569 degrees minus theta 1 was 39.397. 39.397 degrees. When I'll subtract this, 39.569 minus 39.397, we'll get 0.172 degrees. Okay, so this is the angular separation. Oh, so answers are in minutes. So 1 degree is 60 minutes. Oh, sorry. Let me use eraser. Oh, okay. And yeah. So 1 degree is 60 minutes. So when I want to convert this 0.172 degree into minutes, I'll multiply this with 60. I'll multiply this with 60 and I'll get answer 10.32 minutes. Excuse me. So answer is 10.32 minutes. If we only wanted to keep it to first decimal digit, then the answer is 10.3 minutes. So option A is the correct. So angular separation between these two wavelengths will be this. Next question. A parallel beam of sodium light is allowed to incident normally on a plane grating having, this is the diffraction grating. Diffraction grating is 1 over m. Grating element, sorry. Grating element it is called, and this is reciprocal of number of lines per unit length. That is 4250 lines per centimeter. And the grating element is 1/4250 centimeter. And a second order spectral line is observed to be deviated by 30 degree. Calculate the wavelength of light. Okay, we know the condition for maxima. Grating element times sine theta is equal to n lambda. Grating element is 1/4250 centimeter. In sine, this is sine 30 degree. Order, we want second order. Wavelength, we need to find out. It implies that lambda is sine 30 degree divided by 2 times 4250. Now sine 30 degree is 0.5, 0.5, and this remaining is 4250 multiplied by 2 is 8500. 0.5 divided by 8500 is 0.0000588 so on. So when I write, this is in centimeter right now. 1, 2, 3, 4, 5, 6, 7, 8. It will be 588.2 angstrom. Right now this is in centimeter. This will be in angstrom. So B is the correct answer. Okay. Next question, question number 9. Light is incident normally on a grating 0.5 centimeter wide. So the width of the grating is 0.5 centimeter. And total number of lines is 2600. That means number of lines per unit length will be 2600 lines per 0.5 centimeters. That means we don't need to calculate, but this will be the number of lines per unit centimeter. Find the angular separation of the two sodium lines in the first order spectrum. Means we are talking about n is equal to 1. Given lambda 1 is this and lambda 2 is this. So for lambda 1, we will be taking this d sine theta 1 is equal to n lambda 1. D is 1/n, which means 0.5 divided by 2660 centimeter. So this is this. Now sine theta 1 divided by multiplied by d means 0.5, and in denominator we'll have 2660. N is 1, lambda 1 is 5890 angstrom. I'll convert it into centimeter because the D grating element is in centimeter. So in centimeter it will be 10 to the power minus 8. From here I'll get sine theta 1 is equal to 5890 multiplied by 2660 divided by 0.5. This is 31334,800. When I'll take care of this and to the power minus 8, and it will be 1, 2, 3, 4, 5, 6, 7, 8, 0.31 something. So theta 1 will be 17.835 degree. We'll have to use calculator for this. It will be this. Now for lambda 2, using d sine theta 2 is equal to n lambda 2. Again I'll need empty page. Okay. So sine theta 2 being 0.5 divided by 2660, I think. Yeah. And lambda 2 is 5896. 5896 angstrom. So sine theta 2 will be 58, and this I'll put in centimeter. 5896 times 2660 divided by 0.5. That means 5896 times 2660 divided by 0.5 is 313,66720 times 10 to the power minus 8. This is also there, 10 to the power minus 8. Oof. Okay. This is equal to, what is happening? This is weird. Okay. This was lambda 2. Maybe because I didn't save, I don't know what happened. 5, 8, 9, 6, 10 to the power minus 8. And sine theta 2, we got 5, 8, 9, 6 times 10 to the power minus 8 times 2660 divided by 0.5. So out of this, theta 2 we'll calculate, it will be 17.854 degree. So from the grating, the incident light is going. Okay, there are a lot of openings, and here at the center we'll be getting some brightness, and here we'll be getting, corresponding to different wavelength, we'll be getting some order. We have to find out the angular separation between them. So angular separation will be theta 2 minus theta 1, which will be 17.854 degrees minus 17.835 degrees, which will be 17.854 minus 17.835. This is 0.019 degrees. Okay, so again it's in minutes, so I'll multiply it with 60 minutes and I'll get 1.14 minutes. So A is the correct answer. Okay, now last question, question number 10. Here light of wavelength is 5000 angstrom. Okay, where is my cursor? Okay. Light of wavelength we are using is 5000 angstrom. That means, okay, we'll see. The transmission grating has 5000 lines per centimeter. That means D will be 1 over N. That is 1 over 5000 centimeter. What is the maximum number of orders you would get in the transmitted system with the above grating? Okay, so the condition for maxima, B sine theta is equal to N lambda. We need to find out the maximum order for which this grating will give us. This grating will give us what is the maximum number of order we can get in the transmitted system with the above grating. So D we know. Okay, now D will be N lambda. No, we need to find out N, sorry. So N will be D sine theta divided by lambda. Now for N to be maximum, sine theta should be maximum, D is constant, lambda is constant. For N to be maximum, sine theta should be maximum, and we know sine theta maximum value is 1. That means N can be less than equal to sine theta. If it is 1, then the maximum value N can have is D over lambda. And what is D over lambda? So lambda is, sorry, it is, D is 1 over 5000, lambda is 5000 angstrom, 10 to the power minus 8. That means 1 over 25, 0, 0, 0, 0, 0, 0, 10 to the power 8. So 1, 2, 3, 4, 5, 6. That means 100 divided by 25, that means 4. So the maximum order we can get is, N maximum we can get with this grating and with this wavelength is 4. 4 is the correct answer. Okay, so this were the questions related to this week's, where we discussed about the birefringent material and how we get ordinary and extraordinary ray out of it. We talked about calcite material, which is negative uniaxial crystal. We talked about quartz, which is positive uniaxial crystal, how ordinary ray and extraordinary ray have different refractive indices and different velocity in these particular crystals, and thus we get polarized light from unpolarized light when passing through these special systems, and how these different systems can be used in devices, and then what kind of we can use them in retarders. Then we discussed Malus law, then we discussed Brewster's law, and we did questions based on this. Okay, I hope everything is clear to you guys. And if there are no questions, then stop the recording now. And these videos will be available to you anyways. Okay.